Good to see you all here coming out to learn about hurricanes with the amazing Cyrena Arnold. I'm Susie Spickle. And while we wait for a few more folks to show up, we are asking you to put your name in the chat if you want, where you are zooming in from, and your most memorable hurricane. I don't know. That's a good one. If you can't remember your most memorable hurricane, then you can just put in something you want to know about hurricanes. How about that? We'll get started in a couple minutes. And I hope everybody's got their lunch. This is a lunch and learn, so have your cup of, oh, a tornado. Karen Bennett in Antrim says, how about the tornado of 2008? Yeah, I remember that, Karen. It went right
Oh,
through Antrim. It damaged the school, which, yeah, I remember that. That's a good
oh,
one.
we're gonna have to do a tornado talk then, and you guys are gonna really love my next book that's coming out. It'll be available for the holidays. And it's all about tornadoes. So
That sounds really exciting.
yeah,
Yeah.
tornadoes are one of my personal favorites, but hurricanes are pretty cool too.
Why are tornadoes one of your personal favorites?
That's what got me into weather.
Oh,
Yeah, I saw my very first, and actually I have a photo of it here when we kick this off. I have a picture, the very first tornado I ever saw when I was 5 years old, and it's like a switch flipped in my brain.
wow. That's really cool. Where did you grow up that you saw a tornado?
Lots of places, but this was in Colorado, east of the Front Range out in Aurora, Colorado.
There you go. Oh, that's pretty exciting.
Yeah, it was cool. It was awesome.
You didn't travel to over the rainbow.
No, I just saw it just far enough away to give me a very healthy obsession with tornadoes from that point on for like the rest of my life.
And here you are.
And here I am. I know, it's crazy.
That's great. All right, I think we'll get started. We are expecting a few more people, but Serena has a program that's chock-a-block full, so we're getting started. I'm Susie Spickle, Community Programs Director at the Harris Center, and today I'm joined by my wonderful colleague, Brett. Brett, do you want to introduce yourself?
Hi, everyone. I'm the science director here at the Harris Center, and I'll be popping some links in the chat and just generally providing support, maybe answering a few questions if I can in the chat.
I was just going to brag about Brett. Maybe you want to brag about your grandpa because that was so cool. Do you want to tell
Oh,
everyone?
yeah. So one of the reasons I'm really interested in I don't know a lot about weather and meteorology, but we were just chatting before we got started. And one of the reasons I'm so interested in it is that my grandpa Mo was a lifelong meteorologist and a designer of weather balloons. So I feel like I've got meteorology in my blood, and I'm excited to learn more today.
So cool. I just want to welcome everybody to this Zoom and remind you of a few things about our Zoom protocol for the Harris Center. We have everybody muted, and that makes it easier for Serena to go through her presentation. But if you have some questions, you can pop those in the chat. I'll be managing the chat and pulling out questions for a Q&A at the end of Serena's talk. So feel free to do that. Just a quick reminder that we're going to kind of keep the chat focused on the topic and not have a lot of extra chattering going on in the chat because it can be distracting. All right. Before I introduce our incredible meteorological guest, I want to invite everybody to another Zoom that's happening tomorrow night. I'm going to have Brett talk about it since she set it up, but I'm really excited about it. I'll be there too. Brett, why don't you tell everybody what's going on?
Yeah, tomorrow night from 5:30 to 6:30. So instead of a lunchtime Zoom, it's kind of a happy hour Zoom. We are going to be having Dr. Mike Dutton and Helen Dutton from the New Hampshire Center for Veterinary Wildlife. These are folks who are setting up a new organization to help support veterinary training focused specifically on wildlife rescue and rehabilitation, and to provide kind of a centralized location for that in New Hampshire. We have a lot of incredible wildlife rehabilitators here, but we've also had a lot of folks retire from that profession recently. And so the Duttons are working to try to address some of the gaps that have been found. And I just brought an injured bird to a wildlife rehabilitator yesterday, so I'm really excited to hear what they have to say. I hope you'll join us, and I'll put a link in the chat where you can sign up for that Zoom.
It's great. And I'll just give one more kind of ad for an upcoming Harris Center event. Since this is the Lunch and Learn crowd, you might be interested in the next Lunch and Learn we're offering, and that isn't until November 19th, which seems pretty far away, but it will be here before we know it. This is a Lunch and Learn about mighty monarchs, and it's about two women that traveled to Mexico to see the amazing monarch migration, incredible photographs, a story that I think people will really enjoy. And they'll talk a little bit about kind of the troubles that monarchs are having and what we can do as individuals to help monarchs. So sign up for that November 19th. Brett's going to throw that in the link too in the chat. And now I'm really excited to introduce you to Cyrena, who is amazing. I'm going to tell you about her. She wanted to be a meteorologist since the age of 5, and we just found out it was because she saw a tornado and she got kind of captivated by that. And she's had a lot of professional accomplishments, including working with NASA and receiving a certificate of appreciation for her efforts towards aviation safety while employed by them. She installed weather stations on remote Alaska tundra for 6 years, which is amazing. She also was the director of summit operations for the Mount Washington Observatory and was an NH1 News TV meteorologist. Something close to my heart about Cyrena is she writes books for kids about weather. She has 2 great books out there, The Weather Story and The Hurricane Story, and now I'm hearing she's got a 3rd one coming out. Cyrena, want to tell us a little bit about the 3rd one coming out?
Yeah. So you can hear me okay? I plugged my
Yeah.
headphones in and we didn't test that earlier. Great. So the 3rd one is going to be the tornado story, and it's going to be ready this fall. And it's going to teach kids about how tornadic storms form and mostly how to stay safe in a tornado. And as we see climatologically, things are just changing on the large scale. And places are getting tornadoes that didn't before. And so I think it's a really important time for this information, because out in the Midwest and in the plains, they know tornado safety really well. We don't here. And so this book's going to fix that.
Way to go, Cyrena. I don't know how you have all the time to do it because you're writing books, but you're also a storm chaser. So you're out like following storms around, and you're a host of Stormfront Freaks podcast, and you have an incredible Instagram account. So check out Cyrena Arnold, follow her on Instagram. What's your Instagram tag, Cyrena?
Everywhere on social medias, it's at WX Cyrena, WXCYRENA.
That's great. All right, I'm done giving this amazing woman an introduction. She's going to take it away and tell us all about hurricanes of New England. And remember, stay curious and put your questions in the chat.
Excellent. All right, Ken, everybody, are we looking at the big New England hurricane screen? Fantastic. All right, we have a lot of information today. So briefly, why am I the one who's talking to you about this? Then we're going to go over some basics about hurricanes, some of their dangers and things that look a lot like hurricanes. We're going to talk a little bit about the 2005 forecast and talk about forecast accuracy. And then we're going to dive into a couple New England storms of the past, and also talk about our future risks going forward. So that's me, and there's the tornado from when I was a little tiny one, about 5 years old. It was still a funnel cloud at this point. It hadn't touched the ground, but this is what I saw from my doorway when I was about 5 years old, and something in me just clicked forever from that point on. And I've had a very healthy and normal obsession with the weather ever since. And it's taken me to college, where I've worked with NASA contractors. I worked at the National Severe Storms Laboratory. I got to sit in that radar truck collecting radar data from hurricanes as they made landfall. I have worked with NASA contractors and worked in aviation safety and worked with weather sensors that collected weather data, which after being on the Alaska tundra took me to the Mount Washington Observatory. That was just a natural next step. If we're going to be dealing with ferocious weather, there was no better place to go there, which led to a lot of opportunities on international TV with the weather. And being a TV meteorologist here in New Hampshire, which was completely accidental. It just kind of happened. Someone, the station reached out and were like, "We need a meteorologist and we hear you're nearby. You interested?" And I was like, "Sure, why not?" But that was actually a lot of fun. It was great. It was actually one of the places I learned how much I enjoyed communicating weather to people. So after that, I had to grow up and get an office job. And so I've worked at a couple different places. And right now I'm with a company called Atmospheric G2 in Manchester, New Hampshire. And we provide weather data to energy companies, basically, to properly allocate energy resources, know if there's going to be outages or problems, and help them staff resources and things of that nature. I am also a storm chaser. I love taking my annual trip out to the Midwest to see the craziest weather I possibly can. And I have written 2 books, The Weather Story and The Hurricane Story, with a 3rd on the way. So let's talk about hurricanes. Hurricanes are very, very deep areas of low pressure. And one of the first things I want to show you is that when we look at pressure in the atmosphere, it's a lot like a topography map. Now, with this audience, I'm going to go ahead and trust that everybody here can understand what a topography map is and how to use it. Our atmospheric pressure maps are exactly the same. And so if you look at this, you can see that the closer the contours, the steeper the pitch. When you look at your topography map and see how close these lines are, you know that means a steep slope. If the lines are further spread out, you know that's more of a gentle slope. And when you look at high and low pressure are the ponds and river valleys, and high pressure are mountaintops. And if you look at that and understand that, you can see that we actually get this 3D picture of our atmosphere. It's not as flat as everyone would think it is. It has these incredible dips of high and low pressure. These high and low pressure dips correlate to what happens with the weather incredibly well. We'll talk about it in a little more detail, but when you have low pressure, where you have low pressure, you have condensation. Where you have high pressure, you have clear weather. So this looks tropical-ish for me down here in the Gulf. I see some low pressure off here to the west, and I see it up north of the Great Lakes, but throughout the central United States, generally high pressure. If we look at a satellite map, it is not an accident how well that correlates. Cloudy conditions in our tropical something here down in the Gulf, some cloudy conditions to the west and off to the northeast, but where we had all the high pressure, clear and dry conditions. And that is because high and low pressure is the weight of the air above us. It's about 15 pounds per square inch on your body. When there's high pressure, it can be like 16. When there's low pressure, it's about 14. This is why low pressure gives you headaches and gives you joint pain, because when you have high pressure, it is actually like a compression sock or a compression something that you're wearing on your body and makes your body feel really good. When low pressure comes in, people can feel it in their bones because the weight of the air is less, causing your joints to come further apart and actually causing discomfort. The weight of the air changes not linearly, it actually decreases very quickly. So when you go to Mount Everest, which is only 29,000 feet above sea level, they only have 30% of the air pressure there that we do down here on Earth. That pressure drops very, very quickly as you go up in the atmosphere. A little excerpt from the weather story. The air above us is heavy, which you might never know. Its pressure pushes us every day and can be high or low. High pressure brings us sunshine and keeps the clouds at bay, but rainy, cloudy, windy days mean low pressure is on the way. And this is exactly how it looks. Once again, high pressure, the mountain, low pressure, the valleys. And the reason this happens, let me go one step further. Our air is always moving, going from high pressure to low. These differences in pressure are what make the wind blow. The whole reason we have wind is because pressure differentials. And so if you were to take a look at these 2 cylinders, high and low pressure, and join them with a straw and open them up, what would happen? The air would move from high pressure to low. The high would come down and the low would come up. They want to be equalized. They want to be the same height. And so does our atmosphere. And understanding this is a fundamental concept in understanding how all meteorology works, including hurricanes, and understanding where the wind comes from. So wind is just a function of pressure differential. It always goes from high pressure to low pressure and has 2 components, speed and direction. So we know now wind is the pressure trying to equalize. It goes from high to low. The larger the pressure difference, the stronger the wind. So once again, think about that topography map. The closer horizontally you have a river valley and a mountaintop, the steeper it's going to be. The further away they are and the less drastic, the more of a gentle slope it's going to be. The wind follows that slope. The steeper the slope, think of the wind as a little ball bearing or a bowling ball or something you put on that topography map. That is the wind. So thanks to the Coriolis force, because we're on this massive ball of molten lava covered with a thick crust and then put 70% water over top of it and then make our atmosphere a viscous fluid, and we're spinning 1,000 miles through the atmosphere. Because of all that, we have something called the Coriolis force. And it's what causes high and low pressure to spin in our atmosphere. And in the northern hemisphere, low pressure spins counterclockwise. So when you take into account the entire picture of low pressure is rising air, which causes cooling, which causes condensation, which causes cloud formation. High pressure is sinking air. We call the subsidence. With that sinking air, we get a drying out of the air. You get a warming of the air because it gets compressed as it comes down in the atmosphere where it weighs a lot more. When you take this into account with those spin, we start to get a picture of how our atmosphere works. And you could take a look at a map of just H and L's and actually understand which way the wind is blowing and where the risks are, where the bad weather is, and where the good weather is. And so we know that we get this twisting of air and this movement and up and down, and it's a pretty dynamic situation. We're going to come back to this in a minute because this is going to be important in understanding how hurricanes form and understanding how we forecast them. So hurricane season begins on June 1st and it ends on November 30th, with the peaks really being in like August and September. If you look at a map or a graph that shows the frequency, the yellow are just hurricanes, the red are hurricanes and tropical storms combined. You see there's this peak right around September 10th. And it drops off a little slower on the back end, you see building on the front end. And so this is the reason why you see where there's this uptick around June and then it drops here around the end of November. And that's why hurricane season is where it is. So we are at the peak right now. We're really at the time where things should be absolutely most active, yet they are not. Looking at them, at our history here, we had 2 storms at the end of June, 1 early July, a big dead spell. We had Dexter, Aaron, which was a nice Cat 5 in the middle of the ocean all of a sudden. Ferdinand, Gabrielle, which is no longer a tropical storm. Last time I saw, I think it was a Category 4. It's going to be another storm that stays completely out in the ocean. Things have been relatively quiet. We're going to talk about that. So I love cooking and I love baking. And I think the best way for me to describe how hurricanes work is to talk about them like a recipe. So if we were to have a hurricane recipe, this would be it. First, you need warm water. Has to be 79 degrees Fahrenheit or warmer in order for hurricanes to form. Above that water, you need lots of water vapor. The warmer the water, the more water vapor there will be available in the atmosphere. That's the gas form of water above it. The other thing is location, location, location. Dust that comes off of the Sahara, you need just the right amount because it actually forms condensation nuclei. And this is one of the concepts I actually talk about in my book, The Hurricane Story, talking to kids about how the Sahara dust actually forms condensation nuclei for storms to form. So, but like any good recipe, too much of a good thing will ruin it. So African dust, dust from the Sahara is a little bit like baking powder or baking soda in your recipe. If it calls for a teaspoon of it, fantastic. That doesn't mean do a half a cup. That's not going to make your recipe better. It's going to make it much worse. And the same thing happens with the Sahara sand. We need just the right amount of it to form this condensation nuclei to allow water vapor to condense into drops. Every drop has to condense on something. And if you get too much of it, the air is actually lacking water vapor. It's very dry. You have too much condensation nuclei and it can be a pain. The other thing about location is you have to be about 200 miles north or south of the equator. Right around the equator, the Coriolis force is 0. And because of that, storms are not able to form within about 5 degrees. There's one exception, Typhoon Vamai in like 2001 that formed at like 3 degrees. Blew us all away. It was really crazy. Otherwise, that kind of thing just does not happen. So need to be a little bit away from the equator, have this African dust, and you need an unstable atmosphere. You need generic low pressure. You need some rising motion. And you need very low wind shear. Now, wind shear is wind that changes speed or direction with height. And wind shear would basically, if it's too strong, just chops up anything that's trying to develop. If you have a very low wind shear environment, it allows clouds to build and form and for the mechanics to get started for hurricanes to work. So at first you have a tropical depression, whereas we're kind of looking at this organized cluster of thunderstorms that have winds of 38 miles an hour or lower in them. Afterwards, it's going to become a tropical storm. That's when we start to notice a little bit of rotation. We're starting to notice a little bit more of these signals that are getting a little more hurricane-like, and it'll have winds between 39 and 73 miles per hour. And once we have a system that's got sustained winds of 74 miles an hour or greater, we have a hurricane on our hands. Right at the tropical storm level is where the storms end up getting their name. So, you know, Gabrielle, Ivan, any of these storms that we have, this is where that happens. So the typical life cycle for a hurricane, believe it or not, it's actually like 2 to 3 weeks. It's a very, very long process. And what happens is you have this Sahara dust come out over the ocean where it goes over a warm ocean with lots of water vapor in the atmosphere. That Sahara dust hits this moist environment and water condenses on it, starts to form a cluster of clouds and become like a little thunderstorm. With that, we have a tropical disturbance, which is where the National Hurricane Center is like, I've got my eye on you. You're not anything yet, but I've got my eye on you. And not all of them turn into anything, but that's why we watch these. At about 5 or 6 days in, the storm will become a tropical depression. So that's where we're starting to notice some organization, where the sustained wind speeds are really picking up in this. Then it moves to tropical storm, usually about a week or so in. And then if the conditions are right, this is going to get moved up to a hurricane. It'll be a hurricane as long as it's in the Caribbean waters and the Gulf waters off of the eastern seaboard. Once it gets into cooler waters, though, it's going to change how it functions, and it's going to become an extratropical cyclone. And so it gets larger, the wind field spreads out, and usually it starts to lose severity with a little bit of time. And then it'll go across the northern Atlantic and usually wreak havoc in Europe. So when the UK or parts of northern or western Europe get some interesting storms and interesting weather, a lot of times it's from former hurricanes. So to go through this whole process, and as the hurricane story says, the storm starts to march on a path around the sea. It has a very long trip before it reaches you and me. It could be a very, very long time. Sometimes this can be, a 2-week period, and so the entire life cycle can last for 3 or more weeks. So hurricanes on average can really vary in size, but typically they're about 300 miles wide. There are exceptions to the rules. We have had hurricanes that are very small and compact at 150 to 200 miles wide. We've had Sandy, which was close to 1,000 miles wide. They can vary, kind of like breeds of dogs or horses, right? You've got the miniatures and you've got the gigantic ones, but they're all dogs. So same thing here with the hurricanes. Average about 300 miles wide. The eyes are typically 20 to 40 miles across. The eye is the deepest area of low pressure and is a cloud-free location, actually, that clear center that you see in the storm. And the hurricane winds, which are 74 miles per hour or greater, typically extend about 25 to 150 miles in a radius from the eye. Tropical storm force winds can extend up to 300 miles in radius away from that. Like I said, there are some exceptions, Sandy being 1,000 miles across, just absolutely ridiculous. We've had hurricanes that you could almost fit inside other hurricanes multiple times over. And the interesting thing is the size is absolutely no indication of the strength whatsoever. Right? Don't underestimate small ones, right? It's like the little Chihuahua that'll bite you in your ankles and draw blood, right? But the Great Dane won't bother, So size is the bigger the size, it is not necessarily correlating to the strength or severity of that storm. When you look at hurricanes and you look at hurricane forecasts, the thing you have to pay most attention to is what's called the right front quadrant. So imagine the hurricane is a car and you are driving, and the direction it's heading plus its rotation. If you are sitting in the front passenger seat, that is the dangerous side of the storm. And the reason is, and let's see, does this have animations with it? No, it doesn't. The reason is because if this storm is rotating, for math's sake, let's say it has 80-mile-an-hour winds. It's a Category 1 storm, but it's moving at 20. The winds in this front right quadrant are 80 miles an hour plus 20 miles an hour. They're 100 mile an hour over here. Over here, they're only 60 because the wind speed is being subtracted from its direction that it's going. So the right front quadrant has the highest wind speeds. Apologies for dabbing my nose here. We need to rain so bad, and my allergies know it more than anything. This right front quadrant has those combinations, and not only does it have the highest wind speed, but it also brings the highest storm surge. And the storm surge is where the wind pushes water onto land. And the reason it can do that is because you have 100-mile-an-hour wind speeds doing so. So you always have to look at that right front quadrant. Where that right front quadrant is going to make landfall is the most important part. People get very focused on where the eye is going to make landfall. And yes, the eye is a very severe part, but it's a very small severe part. Risks to the right of that eye far outweigh risks that happen to the left. So always have to pay attention to that. Now, hurricanes can bring a whole lot of different perils with them too. We know about wind, we know about storm surge, and we know about rain, but this leads to a lot of other problems. It leads to power outages. It leads to property damage and loss of buildings. It leads to catastrophic flooding. You can have inland flooding and you can have storm surge flooding. And you can also have embedded tornadoes within hurricanes, as if they weren't scary enough. So when hurricanes make landfall, there is a multitude of things to look out for and to watch for. They are broken into category by their wind speed. Category 1 has 74 to 95 mile an hour winds, and they increase with that. Once you reach category 3 or greater, you're dealing with a major hurricane. So the second winds reach 111 miles an hour sustained. We know we have a problem. And then, category 5 is like the 155, 56, 57 range. I get asked all the time, will there ever be a category 6, especially with, climate change and things like that? The answer is no. And the reason is not only does it push the limits of the physics of the atmosphere, which we saw with the hurricane last year. I'm trying to remember which one it was exactly. It could have been Milton when it was grazing just north of the Yucatan Peninsula. Had the most favorable conditions we've ever seen for a storm, ramped up to the highest, one of the fastest intensifying storms we've seen. Not the fastest, but one of. And it reaches kind of a max. The atmosphere has a little bit of a max of what it can do. That's part number 1. Part number 2 of why we never see a category 6 is because 157 mile an hour sustained winds or greater is catastrophic. It doesn't matter. You're actually not going to get a lot of different damage if it's 200 or 210 or 220. 157 mile an hour winds sustained is catastrophic enough that the damage beyond that doesn't really matter. So if you ever want to know if they're going to be a Cat 6, the answer is no. One of the things that's always underestimated too about storms is you hear about hurricanes, and we've talked about the wind a lot. But the absolute deadliest part of not only hurricanes, but all weather is water. Water is the most powerful force we have on our entire planet. And over 88% of deaths from tropical cyclones are due to water alone. We have a massive amount from storm surge that accounts for about half, plus rain, plus surf. And once you combine all of these things together, it's about 88%. So if people are going to have problems, the reason why you have fatalities in these storms isn't the wind. It's always the water. So keep that in mind. And we've seen that over and over again with historical storms. Look at Katrina. Look at the hurricane of 1938. Look at Sandy. You can pull up any historic record, and it's no other peril that causes all the problems. Galveston, for example. It's always the water. So never underestimate that. Never, ever drive through floodwaters. So the reason hurricanes can bring this is because the way the storm moves and operates, with the lower pressure, it can rise up the sea level a little bit, but the biggest thing is the wind. The wind is what pushes this wall of water, this wave of water onto land. And if this correlates at the same time as, say, high tide, the results can be catastrophic. And so this is why it's so important to understand that right front quadrant and understand what storm surge risks are. If you live coastal, I tell people all the time, you have to know your elevation. You have to know your elevation, because storm surge forecasts are really, really good. And they'll be able to say you're going to get 8 to 10 feet of water. You're going to get 15 to 17 feet of water. And it's very, very accurate. If you live at 14 feet above sea level and your storm surge is forecast to be 17 to 18, you have a problem and you have to leave. And a lot of times people don't understand that evacuation does not mean vacation. Sometimes people need to simply move inland by a mile, hang out in a parking garage for a half a day when the storm is making landfall, different things like that, to get yourself to a more survivable situation. Because once again, it is the water more than anything that will cause the biggest problems. And so storm surge is interesting. It doesn't happen in all places necessarily, because it's actually the shape of the coastline that determines how bad the storm surge is going to be. And so the National Weather Service, National Hurricane Center have got great hydrologists employed along with our meteorologists that have been able to map this out and forecast this. And we know with certain storms and wind speeds what that correlating storm surge will be. And so that's what happens, is it just brings that water and it pushes it up into places that it's not supposed to go. Not only that, but the storm surge is moving. I mean, it's not like a flood that happens where the water is staying still. The water is moving along with the storm. And moving water is far more destructive than water that stands still. So typically, actually here to the right is Hurricane Harvey. Hurricane Harvey dumped over 60 inches of rain in Texas. This is a radar image of the 6 days that they received of constant rain. I'm going to see if I can get through this slide before it stops raining in Texas. The average hurricane puts 6 to 12 inches down. In the US, kind of the max we see is about 16 plus inches. And about 75% of the rain in a hurricane falls within 24 hours. Hey, look, it's still raining in Houston. Rain rates can reach about 6 inches per hour in the most severe parts of a hurricane. And like I said, Harvey here that we're watching had over 60 inches in 2017. It's still raining in Houston. Hurricane Helene was also really, really bad. That brought 31 inches to places like Asheville, North Carolina, for very similar reasons. It is still raining in Houston. One of the biggest things that impacts this is, once again, terrain. Terrain can turn rains into catastrophic flash floods, and this is exactly what we saw with Helene in Asheville. Look, it's still raining in Houston. It's actually almost done in Houston. They're still getting a little bit. So what the terrain does is terrible. So in Houston with Hurricane Harvey, for example, the storm sat there for days and days and days and just brought that warm Gulf air and condensed it and dropped it down as rain for days at a time, which was really bad. Houston is also a little bit like a concrete island, very well urban developed, and so the water didn't have anywhere to go, and so it piled up. Places like Helene, it's very interesting because you have mountainous areas, and when that rain falls on mountainous areas, it will run to the lowest valleys. So you can get 4 inches of rain in the mountains, but down in that stream below, when you concentrate all that water that's fallen, that can easily turn into feet of water, feet down below in a matter of minutes. And then it's going to keep following the riverbeds and the places that it typically flows. And this is how you end up with the horrific situations like we saw in North Carolina. So these storms have lots of different perils, as you can see here. Roughly, the category of the storm correlates to certain pressures, which correlates to certain wind speeds, which correlates to certain storm surges. This isn't perfect, but it's a really good idea. If you get a Category 5 storm, you are looking at catastrophic storm surge. You're looking at really bad wind speeds. It's not unheard of to, say, have a Category 2 with wind speeds here, and maybe you get a slightly higher storm surge or slightly lower. This is just a good general sense of, helping you understand that with the increase of categories, the severity of all the different perils that you're going to see is going to increase. Now, hurricanes are really cool because if you're familiar with how a combustion engine works, like the engine in your car, they are incredibly fascinating and work very similarly. So hurricanes are an engine, and warm ocean water is the fuel that drives them. Just like the gasoline is the fuel that drives your combustion engine vehicle. And something that you need to remember is when you have water vapor in the atmosphere, when you have the gas form, in order for it to condense, it has to release heat into the air around it. It has to warm the environment around it. It has to give up some of that heat in order to condense. The opposite happens when you go the other way. When you have water drops and you want them to turn into water vapor, into the gas form, it has to absorb heat from the environment around it in order to have that state change to turn into a gas. That process alone, the condensation and evaporation phase, and the latent heat releases and absorption, is the engine that drives hurricanes. So what happens is the ocean water evaporates and it turns into a gas. As that gas rises, it cools and condenses into water drops. That releases heat into the storm. That heat will rise, cause more water vapor, cools and makes more clouds. And this happens over and over and over again. And it's like an infinite loop. As long as that warm ocean water is there, that process will continue to run. That's why the second a hurricane moves over land, it's done. It doesn't have that warm ocean water, and you basically are completely cutting off the fuel source. When you look at how they operate, they're actually a glorious, incredible, phenomenal, fascinating machine. That you have these different bands of rising and sinking air from that condensation and evaporation process. And it rotating clockwise because of the Coriolis force. And we have this severe eye wall because it's the place in the hurricane where centrifugal force, that force that pushes everything outward, and the Coriolis force are actually in perfect balance. And it's where you get this amazing, beautiful eye that just allows air to keep cycling through and for this engine to keep working. And it's just such a really cool, fascinating process. But not everything that looks like this necessarily is a hurricane. So here's a little bit of a test. Which one of these is a hurricane? A, B, or C? They're all pretty swirly, all a little bit suspicious, all happening over the water. How do you tell the difference? So A is a nor'easter. B is what we call a mid-latitude cyclone, which we'll talk about that. And C is actually a hurricane. And the biggest way you can tell is kind of the closed off eye with the even amount of convection going around it. All areas of low pressure rotate counterclockwise. Nor'easters have that very standard stereotypical comma shape to them. And all areas of low pressure do here in the Northern Hemisphere. And so I want to talk a little bit about some of these differences. So tropical cyclone, Katrina, Milton, Helene, all of these storms are hurricanes. They're fueled by the warm water. The second that storm moves over land, moves over colder ocean waters, it's actually fueled by something different. It's actually fueled by temperature differentials. This was Sandy. Sandy was a hurricane at one point, but when Sandy made landfall and just ravished New Jersey and New England, it actually wasn't a hurricane anymore. It was no longer being fueled by warm ocean waters. It was being fueled by temperature differentials. And when storms go subtropical or extratropical, you lose that balance of the Coriolis force and the centripetal force, and they actually expand and they grow wildly. This is what happened to the 1938 hurricane, and we'll talk about that a little bit later. An extratropical cyclone is a big swirly area of low pressure that doesn't even originate over the ocean. It just moves over land. These are all of the nor'easters that we get. And so all of these are deep areas of low pressure, which is why they rotate counterclockwise here in our hemisphere. And they look very similar, but they are very different things. So Sandy, even though Sandy was a hurricane at one point, and when it made landfall, technically was extratropical, it brought just a ridiculous amount of hazards with it. So we had snow in parts of West Virginia from Sandy. We had massive amounts of flooding, huge beach erosion, blackouts and fires that happened around New York, trees down. Even though it was extratropical, even though it wasn't a hurricane anymore, all the perils that it brings, with the exception of snow, you don't see those in hurricane. All the perils it brought and everything was the same. And so it almost becomes semantics. And so one of the things that we learned with the landfall of storms like Sandy is that a lot of the hurricane messaging stopped when it went extratropical because it wasn't a hurricane anymore. But all of the threats and all of the problems were still there. And so people weren't aware of just how risky it was and how bad it could be. So just because it's extratropical, it's the mechanisms of how it operates that have changed, but the severity of the storm itself will not necessarily. All right, so 2025. Let's talk about what's going on here. When you look at the forecasts that come out, there's a lot of different organizations that put out hurricane forecasts. The company I work for, Atmospheric G2, we put out hurricane forecasts. Colorado State University does, the National Hurricane Center, everybody does. And they're almost always in very good agreement about this is going to be above average season. This will be a below average season. And we do see revisions to this forecast. The first ones usually come out in April, and then it's about monthly where we take another look at it and see. And you could see from like April to July, all of these are forecasting an above average season, but slowly as we've been moving on, the numbers have ticked down just a little bit of what we're going to be expecting for the whole season. As of July, when you took a look, we only had like 3-week storms at that point. There wasn't a lot going on. And so this was the reason why it's like, hey, we're still expecting the season to be above average, but we started noticing some trends about how the numbers had to come down. When you take a look at what causes these forecasts to be either above or below average, there's 2 primary drivers. The biggest ones we see are our sea surface temperatures over the ocean. And then the other thing is, believe it or not, El Nino, the El Nino, La Nina Southern Oscillation. Those 2 big things are a really big key player here. So we noticed in the springtime and throughout the summer, even still now, we have above average North Atlantic warmth. This includes in the Gulf. With El Nino and La Nina, if we have a more La Nina trend, that it actually decreases the amount of wind shear we see in the Atlantic and is known for an increase in hurricane activity. El Nino years provide far too much wind shear over in the Atlantic, so you see a decrease in hurricane activity. So because of the moderately warm conditions and where we were was kind of ENSO neutral, maybe Nina leaning-ish, everybody was in agreement that this was going to be an above average season. And so here's a little bit of explaining why this happens with El Nino and La Nina. La Nina is where we have the cold sea surface temperatures in the Eastern Pacific. El Nino is where they're a little bit warmer. And that correlates to low wind shear in the Atlantic when there's a Nina, or high wind shear in El Nino. And so because of that, La Nina, neutral-ish or Nina years tend to favor more hurricane development, where El Nino years are less. Now we can take a look back at historically. I think this record on the Climate Prediction Center goes back to the 1950s. You can take a look and see if we have had Niñas or El Ninos. And if you go back and take a look at this data, you can see that in 2020, 21, 22, we were Niña. We went to El Nino in 2023, which reason why, if you look back at the 2023 hurricane forecasts, they were definitely below average for the number of hurricanes that were going to form. And we can see forecasts that go out months ahead of time about what we think will happen. And if we're above this line, it's Niño, and if we're below, it's Niña. And so it's staying in that neutral-ish phase, the Niña phase, and looking like we're going to stay there. That's caused the forecasts to be a slightly higher than average season. And then it's the sea surface temperatures. Taking a look and seeing what's happening over here and looking at kind of a neutral zone, some warmer, some colder pockets, but generally speaking, we're right here in this grayish zone, seeing that we were kind of neutral there, that not having El Nino, which is going to increase the amount of wind shear we see over here. Plus taking a look sometimes at some of these sea surface temperatures. If you look at temperatures throughout off the eastern United States, coming off of the coast of Africa through the Gulf, all slightly higher than average. And so when we see that as well, that's all stuff that contributes. So those are the two main impacts. And so when you look at the forecasts and see, this is from Colorado State University, the forecast they made, they started out really high at 17 and have also brought their numbers down a little bit. Now, how accurate are these anyway? Because I'll tell you what, when I do forecasts and I talk about hurricane season and I talk about what's going on and put this type of information out, inevitably I have people always say like, well, they forecast the worst every year, or none of this is accurate at all. And so one of the things I did was I went and I grabbed the data. It's like, let's go take a look and see how accurate this actually is. And so if you look at Colorado State University's accuracy of named storms in their forecast, now this is looking at their April forecast. The orange is going to be what happened. The blue is what they forecast in April. The year with the least amount of named storms was 1983, where there were 4. In 2020, we had 30. So every year they have to forecast somewhere between 4 and 30 storms. And you see the correlation of what has happened versus what they forecast in April is actually really, really high. The average is about 14.4. And there's a couple of years that are exceptions here, like 2005 was an exceptional year and 2020 was also an exceptional year. We also take a look at how this gets better with revisions. And if you look and see how their June forecast changed, how the August forecast changed, you can see in these instances where we have some of these unusual instances, like in 2005, the forecast started low in April, was revised upward in June, upward in August, and you could see where we ended up. And so when you look at how these forecasts are updated, they actually bring them even into more accuracy and make them even better. So named storm forecasts, we do a very good job. With regard to the number that actually make it to hurricanes, in 2013, there was only 2. In 2005, there were 15. So once again, number of hurricanes, they have to pick a number between 2 and 15. And once again, when you look at the data, things trend pretty well. And when we say it's going to be an above average year, it happens really well. And when it's going to be a below average, once again, there's always exceptions, but things look pretty good. And once again, when you bring into account those revisions where you see how seasons change, when things are changing in June and August, and we see that, hey, the conditions are a lot more favorable, the forecasts get revised and are brought even to higher accuracy. And then major hurricanes, in 2013, there wasn't a single one. In 2005 and 2020, there were 7. Average every year is about 3. Remember, that's category 3 or greater. Same thing. You see that the correlations are actually really, really good. So when they're putting out, and then we've got one more, which is the revisions. So you can see when this forecast come out, it's generally pretty good. That having an understanding of sea surface temperatures and also understanding wind shear patterns and all that are very good drivers of understanding what the next seasons are going to look like. So what the heck happened this year, right? So we've talked about how it was going to be above average season. We had everything in place and in favor. We know it was El Nino neutral-ish, maybe Nina leaning. So what's gone on? And there's been a couple things that have been going on. One, the dust that's been coming off of the Sahara has been excessive, and that's putting it nicely. So if you have excessive amounts of dust, once again, going back to that recipe, it's too much baking powder in your recipe. It's not making better cookies. It's making really awful cookies that nobody wants and taste terrible, okay? It doesn't work. Same thing. Far too much dust coming off of the Sahara, which is giving us drier conditions, and too much condensation nuclei coming off of the coast. The other thing we've seen is a little bit too high of wind shear in some places. And a lot of that also has to do with a oscillation in our environment called the Madden-Julian oscillation, which is what this graph over here on the left is. And there are these semi-permanent areas of high and low pressure that move east along the equator and the area of the equator. And depending on where this sets up, it's about a 30 to 60 day cycle. We have actually had it to where we are in the unfavorable conditions during the peak and the best time here of hurricane season. And so because of that oscillation, it's kind of been inhibiting things and putting the lid on it a little bit. Now we are starting to move into a more favorable environment for that, for the Madden-Julian oscillation. We still have warm ocean waters. There's a lot of meteorologists think the end of the season is not going to disappoint, that the end of the season is going to be making up for what we have lacked so far this summer. The other thing is the Bermuda High, and there's kind of a semi-permanent area of high pressure over the Atlantic, has been moving a lot and has been higher than the normal at times and has been oscillating a lot. And because of that, you're not getting the rising air that you need for clouds to form and to turn into clouds and to have that condensation process. So these are a couple of things that are going on right now during the peak of the season that have been a little bit inhibiting. But things are slowly fading away into more favorable environments. And the question is just how much of the end of the season is going to make up for what we have lacked during what should be some peak times. So it's going to be interesting to see how this plays out. So what about New England? I mean, we're not in Florida, right? We're not the peninsula jutting out into the middle of the ocean where you're more likely to get hit than any other state. What is New England's risk? The interesting thing about New England is wherever a weather system originates in the United States, it almost always exits over New England. This is one of the things we talked about on Mount Washington all the time. And when you track storm tracks over a very long period of time, Pacific Northwest storms exit over New England, Southwestern originating storms, New England, Southeastern and Gulf storms, New England. Now, a lot of this has to do with the position of where the jet stream is in relation to that high and constantly steering weather right over us. And there are some exceptions to that rule. Take a look, example, for the past 2 months. Why have we gotten no rain? Because things are not exiting over us right now. Things are going to be moving back into that, which is why we're finally getting some rain this coming week, because everything is going to be exiting over New England. But we're not free of seeing storms. This is a map showing all the different hurricanes that have impacted New England. And if you take a look, one of the biggest trends is that they're all almost originating here throughout the ocean and on the Western Atlantic coast. You don't see a high number of Gulf originating storms impact New England, which is very interesting. When you look at some of the past storms, going back to 1960, and I will go back to the 1938 storm, you see we've had our fair share of actually some really bad ones. We've had Donna in 1960 that was a Category 4. Belle, Gloria, Bob, Lloyd, all these reached their peak intensity and were really, really strong storms. When they made landfall, though, we're looking at Category 1, Category 2 storms with Donna, with Gloria, with Bob. And if you go back to the 1950s, there were even more storms. There was Carol and Edna in 54 that were 11 days apart, both Cat 3s that made landfall in Connecticut and Martha's Vineyard. And so we've had our fair share of storms, and a lot of these have been tropical storms. Henri in 2021 was a tropical storm. Sandy, once again, wasn't a hurricane technically anymore. That was extratropical. Irene in 2011 was a tropical storm. Bob was a Cat 2. Gloria was a Cat 1. Carol and Edna in 54 were Cat 3s. We've had some good ones and some interesting ones in the past. And so a book I just finished reading was called Taken by Storm, which was a detailed history of the 1938 hurricane. This was a Category 3 storm, was responsible for over 700 fatalities, and is a really, really neat story. The book I read was written by Dr. Lourdes Aviles, who's a professor at Plymouth State University, and she's one of the biggest experts on this storm, and it had some really, really fascinating information. And I see some things as they pop up in the chat every once in a while. I remember someone asking, I saw something there about why the storm went the way that it did, as it popped up briefly. And one of the reasons is because there was a deep area of low pressure to the west of New England. And where hurricanes go is going to act a lot like a bowling ball down a bowling alley. And if you put the bumpers up, those are areas of high pressure, and it steers storms away. Areas of low pressure, say where the pins are, if that's an area of low pressure, it's going to go down in elevation. So if you roll a ball, where's it going to go? It's going to avoid the bumpers and it's going to go down the hill. And when you have this trough that was in place, it was basically like digging a trough for the ball to roll straight down to. And so it came around the high pressure, the semi-permanent high pressure we see over the Atlantic, and crashed right into New England. Over 700 people died from this. The anniversary of this was only 2 days ago, it was on the 21st. 1,800 people injured. 5,000 buildings were destroyed, 15,000 damaged, and 80% of all the electricity lines in New England, all of New England, were taken down. It was something to the equivalent of like 22,000 miles of electricity lines were damaged, which you could almost go around the globe with. Like, right, the equator is 24,000 some miles. I mean, you could have almost gone all the way around the globe with the amount of lines this thing took down. One of the most amazing things about the Great Hurricane of 1938 is that it took down 50 million trees. And that was a lot. In fact, the lumber market within a matter of days had added to it about 5 to 10 years worth of lumber production added by a single storm. Really interesting stories around that. What led to some of the devastation with the 1938 hurricane is that it was a very wet summer. Almost all areas in New England had received 125 to 150% of the amount of precipitation they're supposed to get for that time of year. That week alone, before it made landfall, there was 4 to 10 inches of rain recorded throughout the area. And so of the 50 million trees in New Hampshire alone, 75% of those were white pines. And pines are known for having a very shallow root bed, grows outward, doesn't go very deep like other trees. All the pine trees and evergreens have very shallow root beds. And so when it's very, very wet and you get these high wind speeds, they're more susceptible to loss. And so when you look at how wet the summer was, how wet the week was, and then this is a storm that moved at an incredible rate, very high wind speeds, made its way very far inland and just caused damage like no one had ever seen in New England before. The area with the most amount of rain from the storm was actually in Hillsborough, New Hampshire, pretty far inland, wasn't like the coast, at 7.36 inches of rain. And the wind speeds at Mount Washington Observatory, they observed 118 mile an hour sustained winds with gusts to 163. And at Blue Hill, 121 sustained with gusts to 189, but the anemometer broke. That's pretty cool stuff. So what happened is this storm was moving at an incredible pace. It was moving at about 50 miles an hour, which is very fast for a hurricane, unheardly fast, like ungodly fast. And as it made landfall, it was transitioning to an extratropical storm. So it was no longer being fueled by those warm ocean waters anymore because we were up in New England, it was coming over land. As we talked about earlier, as it was going extratropical, its wind fields expanded. They were just as strong, but they got a lot bigger. And so this is a storm where it was a little bit like the perfect storm, but not the perfect storm, where it started going extratropical, right? It was making landfall, moving at 50 miles an hour. And so you had wind speeds make it inland like you don't see with storms like this typically. The storm surge heights, I circled just a couple of them that I thought were interesting. West Haven, Connecticut had a storm surge of 16.6 feet. Marion, Massachusetts, over 18 feet. And Rhode Island had some ridiculous storm surge. And people are telling me that when you walk around a lot of coastal towns in Rhode Island, they even have plaques on a lot of the buildings showing the water height where it was. But seeing 21 feet of water in Newport, Rhode Island, 26 feet in Portsmouth is just mind-boggling. This storm was so strong, it absolutely altered the coastline. And one of the things that made this super interesting was that 1938 was a time of time anarchy in the US. Everyone was fighting about whether to use daylight time or standard time. And states were going rogue, and even towns within states were doing their own time. So this was a storm they didn't get a lot of warning about. And the few warnings that came out, people didn't understand if it was going to be happening now or an hour from now or when it was, because of kind of the craziness that was going on with the time systems. So what went wrong with this storm? Well, we didn't have the observations that we do now. Mistakes that were made then aren't made easily anymore because we have a great observation network, we have satellites, and we have radar. One of the things they did have to help forecasting at that point was ships. Ships would radio in when there were storms. They could tell you sometimes the direction it was heading. They could tell you what observations they were seeing, what was the wind speed, what was the direction. The problem is once a storm was known, ships started avoiding it. So you had this interesting thing happen with storms that were happening during this time before our technological boom, where once a storm was known and started getting severe, ships started to avoid it. So then we started losing observations. And so we knew less about where it was going because people knew there was a storm there and they didn't want to go there. The other big problem is that there were a lot of assumptions from the DC office, and they were very much of the opinion that hurricanes avoided New England. All of them that they'd ever seen have always gone off and curved off and gone to the Northeast around the high pressure and sailed across the Atlantic and haven't been an issue. And this one was a lot different. And it's what we know about hurricanes today that make this kind of mistake not possible to happen again. And once again, it's also that 50-mile-an-hour speed. I mean, in one day, it basically traveled from the latitudes of like the Carolinas to New England, you know, from that morning to that evening, which is just really ridiculous and unheard of. So there was a lot of things that went wrong with the storm, but it is a record-breaking storm and is one of the most deadly and dangerous storms to impact New England, more so than Irene and more so than Sandy, which we know more so in recent times. This one was really, really unique and really special. So what's our risk? Right? Like, it's happened before. Can it happen again? And one of the nice things is, you know, there will be a year, there will be a time. We know statistically speaking, a storm like the 1938 hurricane has about a 150-year return period. So on average, if you look back, there was the really bad storm in 1938. There was a really bad one in the 1800s. There was another one in the mid 1600s. We have historical data and information to know that the return period is like 150-ish years. So doesn't mean it can't happen, just helps you understand our risks. You know, it's been 87 years, so it's interesting to see what happens in the future. When we look at what was going to go happen this year, and we looked at the typical high and low pressure areas, we could tell that we were going to have more of high pressure located over the northeastern United States. And once again, think of the bowling and you pop the bumpers out. High pressure is great for avoiding hurricanes. And so knowing that we've got this little bit of more high pressure here in the northeastern United States for this time of year, for the season, with the current setup we have with El Nino and La Nina, it kind of acts as a little bit of a protector for us and a little bit of a barrier. And you typically see lower pressure throughout the Caribbean islands and through the Gulf. And so on a year like this one, we know storms are going to be slightly more favorable if they're going to impact land to be more Gulf Coast originating. And so we know that this is typically what we see in years that look similar to what we have this year. And as you go through and look at what the forecasts were for June, for July, for August, for September, you see that, you know, bright red area over the northeastern United States, which is that area of high pressure, which is very protecting. Good news is it helps to keep hurricanes away. Bad news is why the last 2 months have been very dry. So it's kind of like a give and take kind of relationship here. We're not completely free. And if you look at forecast long-term tracks and long-term patterns, if there's going to be something that's going to have more of a northerly or northwesterly component, October is actually that time frame. And when you look at timing of some of our bigger storms, a lot of them are more of the right after peak season time frame that they're impacting the northeastern United States. So we see the steering currents in August and September typically push things away. And if we're going to see a change and we're going to see a time where the risk in New England's a little bit different, October is kind of when that is. So a couple tidbits here just to wrap it up, and then we'll get to some questions. One of the most popular questions I get all the time is, what's the difference between hurricanes, typhoons, and cyclones? They're the exact same thing. The difference is where they happen. So hurricanes happen in the Atlantic and in the Eastern Pacific. Typhoons happen in the Western Pacific, and south of the equator in the Indian Ocean and Southern Pacific, they are cyclones. Same mechanisms, same storms. The only difference is because cyclones are south of the equator, they rotate clockwise. That's the direction low pressure goes down there. But these are all the same mechanisms and the same types of storms. Some of my few favorite hurricane facts. Hurricane was the Mayan god of windstorm and fire. It's where the name hurricane came from. Every second a hurricane releases the energy of 10 atomic bombs. They're such awesome engines there, and they're so big and so powerful. It's very interesting. The deadliest hurricane in U.S. history is Galveston, September 8th of 1900, where between 8,000 and 12,000 people died. I love this one. When the National Hurricane Center began giving storms names in 1953, they were all female names. And then in 1978, enough people complained about that and they made them male and female. Extra fun thing that I actually need to add to this is there's been research done to where male name storms versus female name storms, there is a significant statistical difference in how serious people take storms and whether they evacuate or not, whether they're male versus female named. People take male name storms more seriously than female name storms. Really crazy stuff. Susie's like, this is one of the craziest things I've ever heard. But there's research behind it, data behind it. And then lastly, anything that happened before the 1970s, before the satellite era, both of the two major storms that we've had, Gabrielle going on right now, and the earlier one, the other Cat 5. Cat 4 is Gabrielle's Cat 4 right now, and then there was another Cat 5. I can't remember the name of it. Would have never been noticed before the 1970s because they've stayed out to sea. You might get a couple ship observations, but that's about it. And so it's really the satellite era in the 1960s that really helped us track this storm, track all of the storms, where before we'd only see things that would make impact on land, which is very fascinating. So anytime you look at data or statistics before the 1970s, you kind of always have to keep that in mind and understand that data sets from the 1960s may not be complete. So there you go. If you want hurricane information during the season, the best way to get it is go to the National Hurricane Center. You can type in, I think, hurricane or hurricanes.gov or nhc.noaa.gov. They have a lot of really great information. And then I always like to leave people with the difference between a watch and a warning as we get into flood seasons, as we get into winter weather season. Watch and warning can be very confusing. What's the difference between a watch and a warning? Watch means it may happen, and warning means it is happening. The easiest way to remember that is this is a cupcake watch. This is a cupcake warning. Remember that for your future events and you'll have nothing to worry about. But that's it. This is how you can find me, my website, email address, socials, all of that information. I do have the third book, The Tornado Story, coming out this fall. But yeah, let's use any time that we have and anytime you guys want to answer questions that you've got about hurricanes. There's a lot of information in a short period of time.
Wow, Cyrena, thank you so much, and giving you a big applause over here and thumbs up. That was so
Thank
much
you.
great information and fascinating. And there were just a lot of questions were answered as they came up. But there was a question from Karen, and I also wondered this. Does it always take African dust, or can something else be like the condenser?
Yeah. Condensation nuclei can be a lot of different things. It can be dust, it can be particulates, it can be ash, volcanic ash. Any of those little tiny small things floating around through the atmosphere can be condensation nuclei. The Atlantic basin has that Sahara dust that acts like a really, is a big piece of the puzzle for us. But once again, you've got to have just the right balance. Otherwise, it's inhibiting like we've seen so far this year. But it doesn't just have to be dust. It can be a lot of different things. And when you take a look at the other hurricane basins or tropical storm, cyclone basins around the globe, the first most active is the Pacific. The second is the Indian Ocean, and the Atlantic's actually third. I mean, we actually see the country that gets the most landfalling hurricanes or Cat 5 hurricanes is the Philippines. We get, I think it's like about a quarter of what they do. And they don't have Sahara dust flying around over there. So it's other things. It's any particulate matter. It's volcanic ash. There's a lot of different sources. So yeah, it can be a multitude of other things.
Great. Okay. This question I'm curious about. I'm sure other people are too, but I'm curious about the impact of our changing climate on the future of hurricanes.
Yeah, that's a good one. One of the things that we are seeing far more than anything is the frequency that rapid intensification happens, where every season there's another storm that's broken a record for how quickly it rapidly intensified. And it's because all of the conditions are there. Everything is warm. The ocean waters are very warm, which has more water vapor to them. And if you happen to get a good time where you have low wind shear and all of those ingredients are coming together just right, it is like dropping a match over over a gas can. And so we're seeing that happen with more frequency. We're seeing more rapid intensification than we have before, more instances of it, and happening faster. There was a storm that happened, it was Otis. It was actually in the Pacific and hit a Pacific town in Mexico. And then which one is, I can't, isn't coming to my brain right now. Otis went from a tropical storm to a category 5 in 12 hours. I can't express the significance and how substantial that is. Nobody forecast it. Forecast models are really bad at rapid intensification, but it seems to be happening more and more. And a lot of reason is because of changing climate. The models were built upon a climate that was different before. So we know where hurricanes are going to form. We have a really good sense of where they're going to go. Intensity forecasts have a lot of room for improvement, especially with that. And that's one of the hardest things to keep up with in one of the areas we're seeing the biggest changes. So you're going to see storms that are getting stronger, faster in a new environment.
Wow, thank you. Thank you, Cyrena. I'm noticing that you answered all the questions that came up during it. So such a great job. Thank you so very much. That was stupendous. And I'm definitely going to be in touch with you for a tornado talk.
Yeah, that'll be great.
Yeah, that'll be great. So thanks for everybody who tuned in, and everybody's saying they can't wait for their tornado talk. So we'll be in touch. And until then, everybody stay safe. And remember, if you got the warning, you better get your cupcakes in order and get out of Dodge. Right?
Right? Exactly. The difference between watching and warning is life-saving, right? Watching may happen, warning, it is actively happening. I love this graphic. It will honestly make a huge difference for you anytime there's severe or notable weather.
It's making me hungry.
Fair, fair.
On that note, thank you again, and thanks to everybody, and we'll see you at the next thing we see you at. Bye.